I'm almost done grading the midterm. I think I'll be able to turn it back on Monday. I'm pretty sure I will. I think it went all right. I thought I'd go over the exam today just to get that over with. Today's lesson is about continuous functions. That's the new chapter, chapter 5, starting with 5.1. Are there any questions about anything? Let's see. Yeah, so I'm going to go over the exam quickly. The first problem was just to compute a limit. So you'd have to show your reasoning, but you didn't have to turn it into a knockdown, drag-out proof. So we've seen this difference of square root things enough that the trick, I think almost everybody got the trick that you multiply by 1 in the form of the sum of those two things, so that when you multiply them together, the numerator becomes a difference of squares. And when you do that, a miracle happens in the numerator, and the n squareds cancel, leaving you with only n minus 1 on the top. Which is quite simple, and it's also it's no longer some negative stuff to deal with. Everything in this thing is going to be positive. And in the denominator, you get the sum of those square roots. Okay, and if you think about what the biggest power of n in those two things are, n to the 1 is obvious on top, and the square root of n squared on the bottom is also an n to the 1. So you'd think that that's going to behave asymptotically, like n over n plus n on the bottom. And that to demonstrate that feeling, this is a kind of a thing you learned in freshman calculus. So people knew this first step about the difference of squares much more commonly than the next step, which is to multiply the top and the bottom by the fraction that isolates the top order term. Okay, so if the top order term looked like n in both of those, then the thing to multiply is 1 over n, top and bottom. That gives you a 1 minus 1 over n in the numerator, and when you distribute through the square roots, you get something that clearly converges to, let's see, on the top, it converges to 1 minus 0. And remember, we've proved something that if one of the laws of limits was, that the sum of limits is the limit of the sums, etc. But we also had a law that said that for positive terms that converge, the limit of the square root of n is the square root of the limit. And using that on the bottom, that first square root would converge to 1 square root of 1 plus 0. And the second one would converge to also 1 plus the 0 squared square root. And so the whole thing converges to 1/2 as n goes to infinity. Questions about that one? That mostly went pretty well. Yeah, since the test was about the whole semester, you were allowed to use the laws of limits to avoid using the definition of limits. Let epsilon be 0 and then look for an n. Let epsilon be bigger than 0 and look for an n that makes that minus the limit less than epsilon. That would be kind of tedious. So the rules of limits make that a whole lot more manageable. And you were allowed to use those. The next one was just if you know the fact, 2a was just knowing the fact that c to the 1 over n tends to 1 as n goes to infinity if c is greater than 0. And so for c equal 2 and c equal 3, of course, both those limits are 1. And then we studied the famous sequence 1 plus 1 over n to the n that converged to e, we determined that it was an increasing sequence and it was stuck between 2 and 3. So it's bounded above, that means it converges. And the limit would be less than or equal to 3, but turns out it's less than 3. So E is between 2 and 3. It's about 2.7 something. And that, so you would know if I put an n squared where the n is in the series, in the sequence, that would be a subsequence of the original. And so that subsequence would also converge to E. You don't really need that fact. You just need to know that all those numbers are between 2 and 3. And so part A was kind of screaming for the squeeze theorem. You got that inequality there. And so if you were to take 1 over n powers in that inequality, you get that 2 to the 1 over n is less than 1 over n power of that thing in the middle, which is exactly what I asked you to analyze. That's when you take the nth root, the exponents multiply. And so n squared times 1 over n is n. And so you get 1 plus 1 over n squared to the n in the middle there. And now you've got those squeezed between two sequences that both tend to 1. So that one also tends to 1. Questions about that? I guess the feeling, the squeeze theorem is how you demonstrate this fact, but the feeling is that 1 plus 1 over n squared to the n squared is tending to e, and so you would expect the thing we're supposed to study to look like e to the 1 over n. And e to the 1, e being between 2 and 3 is positive, so you would expect it to go have similar behavior to e to the 1 over n. And you could turn that into a proof by doing careful estimates, etc. But it's not as scientific as using the squeeze theorem. Questions about that one? This was just a straightforward use of the geometric series facts. The problem in part 3a was to compute that sum as capital N goes to infinity. And it doesn't start with the usual the 1 term plus r squared, etc. It starts with a 5th power. Well, the key to understanding how to deal with that is to factor it out. And so when I factor that out front, I would get a geometric series, and I could use the famous formula for that geometric series that is explicit sum of that series. And I got, there it is, n minus 5 plus 1 would be n minus 4 in that power on the numerator. And we know that r to the n goes to 0 if r is between 0 and 1. So that 1/2 to the n minus 4 is going to go to 0, and we're left with 1/2 to the 5th over 1 minus 1/2, which is 2, so it's 1 over 2 to the 4th, which is 1 over 16. Questions about A? That one went pretty smoothly. You can also just quote the fact that a geometric series where r is between 0 and 1 tends to 1 over 1 minus r. You could quote that fact if you didn't want to do it. If you didn't want to put that n there and let n go to infinity. You quote that fact about geometric series. Well, that was a hint for how to do B. So in part B, you got 10 points if you, or 5 points rather, if you could state what it meant to be a Cauchy sequence. And then 5 more points if you showed that for the case of these partial sums of this geometric series. So let's see, did I write what Cauchy means? I didn't. Let's see, so given epsilon bigger than 0, we want to find a positive integer so that if n and m are both bigger than the positive integer, the terms are really close together, Sm minus Sn. I want to make that difference less than epsilon. Well, you can write out explicitly what that is. I like to assume that my m is the big one. Doesn't matter which one's the big one. But if I write Sm minus Sn, that would cut off the beginning of the sequence out to n. And I'd be left with a geometric sequence that starts at r to the n plus 1 and goes out to r to the m. And like in part A, I can factor out that first term. Actually, lots of people use the sum formula for Sm and the sum formula for Sn and subtracted them, and that worked great. Maybe better than what I'm doing here. I wrote this before I graded anybody. Anyway, you can get an explicit formula for that thing that's short and sweet because of the geometric series formula. And here I have it. And I want to make that less than epsilon. Okay, so the question is, how big does that n have to be to make that less than epsilon? Well, let's see. Notice that I have a thing there that's an r to the m minus 1. That's subtracting something on the top. And even though that goes to 0, that's strictly less than r to the n plus 1. What? Did I miss that? Oh, yeah. That thing on top is less than 1. So I can estimate that and get that the difference is less than r to the n plus 1 over 1 minus r. Okay, and that thing on top goes to 0. So I can find an n such that r to the n plus 1, being less than epsilon wouldn't be enough. I want it to be less than epsilon times 1 minus r, so that I can make that thing cancel and get left with epsilon when n is bigger than or equal to capital N. Hence, when I do that, I'd get that the Sm minus Sn is less than epsilon when n and m are bigger than n. And that's what it means to be a Cauchy sequence. Questions about that? Number 4 was just to see if you knew what the supremum is. If a set is bounded from above, the supremum of A is the least upper bound of A. And it was one of the big moments in the class that, we had to assume that that's a basic axiom of the real numbers. Dedekind demonstrated it by telling you what a real number really is. But if you don't do that, you have to realize this least upper bound property is one of the basic axioms of the real numbers. And the word for that is complete. So you could either use the term the least upper bound property of the real numbers or the fact that the real numbers are complete. That's what I was fishing for there. So that's state why it exists. Question about that? It was worth 5 points to somehow say that that's a fundamental principle of the real numbers. And that's why it exists. Questions about 4? And 5 was just to recount the famous proof. I mentioned that this was a possible thing in the practice problems. The famous Cantor's proof was, if that was a countable set, there'd be a one-to-one onto mapping of the natural numbers to the interval 0 to 1. And if I let r sub n be the phi of n of that map, then that should pick out all the possible real numbers between 0 and 1, if this thing is countable. And so the Cantor trick, for the first term, pick a closed interval that's in A1 that doesn't contain the first R1. And of course, A1 needs to be less than B1 so that that's not just a single point. And next we pick R2. Let's see, R2 might be in that closed interval A1, B1, or it might not be. But either way, I can pick a closed interval that doesn't contain R2. That's a subinterval of that A1, B1. And I can keep doing that. And then I get this nested sequence of closed intervals that are in subsets of the 0, 1 closed interval. And the closed interval theorem says that that intersection of all those things contains something. So let's say R is in that thing. And if you look above, I have that R would be in AN, BN, because it's in all of them. But remember, RN, the AN, BN was chosen so that RN is not in AN, BN. So that means that R couldn't possibly be equal to Rn. And that's true for each n. Hence, that R doesn't get hit by phi, and that means that phi is not onto. So my assumption that there was such a mapping is wrong, and we conclude that interval from 0 to 1 is uncountable. Question about that one? That's straight out of the book or out of the lecture notes. Any questions about the exam at all? Yeah.
For the last one, I use a different expression, but just assume it's about like it's a very close interval, and I on the book.
The nested closed interval theorem?
Yes.
What did you say it?
So I represent the xy 0.x1 1 1 1 2 2 1 and
Oh, I bet it sounds right. I'll have to just look at it.
yeah, it's from the book. It's
Okay, if it's the way, yeah. I mean, if I asked you to use the nested closed interval theorem, Cantor had another proof using decimal expansion.
Oh,
That that would be a different proof than I was asking for. If that's what you did, I'll have to think about it. Okay, that's enough of that then. So on to today's material, which is about continuous functions. You learned the definition of continuous functions in freshman calculus. So f is continuous at C if the limit as x goes to C of f of x is what it's supposed to be, named f of C. So no jumps, no sneaking out of what it's supposed to be. So that means that given epsilon bigger than 0, there is a delta bigger than 0, such that f of x minus f of c is less than epsilon if, remember in the definition of limit, we always said x was close to c, but not equal to c. But now we don't mention anything like that. We say that if x minus c is less than delta. Okay, well, that's the freshman calculus version of it. Well, you might think, well, what does it mean if C is the left endpoint of an interval where the function's defined? The statement would still be exactly the same, but I would have to say that X is in the set where my function is defined. So, question is, what if F is not a function on, let's say, a whole real line, but a function of A into the reals, where A is some subset of the reals. Well, then, if you think about graphing it, let's pick an A. I'll have an A point in A that's just an isolated point like that. And then I'll have an interval in AB that goes from A to B. And then maybe I'll have something like a sequence like 1 over n. Let's see, how about this? Piling up right there. So let's call this an x naught. And a continuous function on that thing might, right here, it just might be a value. And so being continuous at x naught, which is an isolated point in A, this red set is the A. Wouldn't make sense. I mean, anything's continuous. You can give it any value there. When you get close to x naught, which there is only one x naught that's close to x naught, that's x naught. So whatever value it is there, it certainly is a continuous at that point, x naught. And then on AB, you know what it means to be continuous. At the left and right endpoints of AB, it would have to tend to the right thing for it to be continuous there. And then this one, in the limit, these would have to pile up really close to the value there to be continuous. So at cluster points, so here's the thing when you think about it and draw this picture. Let's see, why don't I make something else over here? I could have a closed interval. That's a closed interval AB. What if I had an open interval CD? C and D are not in the set, so we don't care about what happens there. So for example, something that blows up at the edges here would be permissible. That's continuous on CD. And since the endpoints are not in there, we don't care. So that's a picture. And I want to say a definition that includes all parts of that picture. Yeah, so those are supposed to pile up. At the dot. Okay, that's what continuous functions look like. So you notice that the only time something interesting happens is if the point I'm talking about is a cluster point of A. So x naught is an isolated point of A, which is the same as saying it's not a cluster point or accumulation point. Okay, and then f of x naught could be anything, and it would be continuous. Could be anything. f is continuous at x naught. But all those other points are cluster points of A. If C in A is a cluster point of A, then being continuous at C would mean given epsilon bigger than 0, there is a delta such that f of C, f of x minus f of C is less than epsilon when x minus C is less than delta and x is in A. So that's the new thing to add if you're talking about sets that aren't intervals. And of course, the definition you know from freshman calculus is that f is continuous on a set if it's continuous at each point in a set. F from A into the reals is continuous on A means f is continuous at each point in A. Let's see, I guess you draw the usual pictures. So here's the geometric meaning of continuity. And when you're doing these geometric meaning, you think of epsilon as like an error or tolerance. Epsilon as an error. Or if you're an engineer, tolerance. How close do you have to get to something to get within a tolerance of epsilon? Okay, so the geometric meaning would be I'll have an f here. Let's say I have a f, this is going to be f of C right here. And then I got to be within epsilon of that. So I'll make a dotted line here of plus epsilon. And a dotted line of minus epsilon. Okay, so this top one would be f of C plus epsilon, and the bottom one would be f of C minus epsilon. And here's C. And let's say my function, let's see, I want to get a thing that looks like steep. Oops, that's no good. I want it to be steep from the left and then kind of go like that to the right. If you think about what delta would squeeze my function f of x into that tolerance band, I can see, aha, well, this side I better be really close, but the other side I could be a mile away and it would still be within that tolerance. But the delta is symmetric, so in this picture, the delta that would work would have to be pretty close here. And so consequently, it'd have to be close to the right, too. So that would make this ... The f of c needs to be, the center, it needs to be f of c. And then the delta here, because to get it squeezed on the left, it has to be really close, which means consequently, I've got a lot to spare on the right. That doesn't look very good. Anyway, look at the picture in the book. It's easier to look at than this. I could find the best possible C, but you don't have to find the best possible C. I could squeeze it down even smaller and just get a C that works. Questions about that? That's the picture. And so another way to say it is that, so here's kind of a topological way to say it. Topological way of thinking is that there is a delta, given epsilon bigger than 0, there is a delta such that f of the little neighborhood interval, v delta of c, is contained in v epsilon of f of c. That's exactly the same thing as in the picture. And topology talks in terms of open sets. And those little open intervals are the basis for open sets. So actually, continuity in a topological sense means that exactly that. Let's see. So the book shows you some examples of continuous functions, the usual ones, and the usual ones that aren't. I thought I'd explain a wild and crazy function. It's called Tomei's function. Okay, and here's how you cook it up. Let's see. We're going to let the Tomei function, let's call it t of x. Let t of x, so this t of x is going to be defined on 0, 1 into the real numbers. Let t of x equal 0 if x is irrational. This is a fun thing. So that's easy. But what if if q is rational? If x equals q, let's write it as p over q is rational. Let's see, then, there's a unique factorization theorem. I can factor p and q and then cancel out all the common factors. Can write x as x equals p twiddle over q twiddle, where p and q are what's called relatively prime, meaning all the common factors have been factored out. So where p twiddle and q twiddle are positive integers. And this is a unique way of writing the rational number, where p and q are positive integers with no common factors. There's a fancy word for that in number theory. They're relatively prime. Okay. Then the Thomé function t of x is equal to 1 over q twiddle. Those p's and q's are uniquely determined, p twiddles, because there's only one way to express them as p over q with no common factors. And a mind-blowing thing is that this function is continuous at every irrational number. So if you tend to an irrational number, those rational numbers that are close by, the q twiddles have to get bigger and bigger. Think about, what if there was a 4 in the denominator? Well, there's only a few points that are have a fourth. It's 1/4, 1/2, 3/4, etc. And so if I'm not close to those, then the next possible is a fifth. And then you think about, okay, there's only 5 spots that have a fifth in the bottom. And if I'm not close to one of those, which I'm not, it's irrational, I can shrink down my delta a little bit, and so I wouldn't have any 1/5 ones. And I can do that again and again until I make the q twiddle as big as I want. So the book writes out that carefully, but here's a cool thing. T is continuous at every irrational point. In 0, 1, and discontinuous at every rational point. I should have mentioned here is let t of 0 equal 1 and t of 1 equal 1. Because then those are 1 over 1. Yeah, I guess that makes sense. 1 over 1 is the way to think about those. That's a neat thing to think about. And yeah, when you think about it, there's finitely many places where you could get like a 10 in the denominator. It's the numbers that look like multiples of 1/10. And so you make your delta small enough that you don't have any of those in there. And then the next one you would think of being 1 over 11. And you might have to shrink it again until you get to 1 over 1,000. And you would shrink it until you don't have aren't anywhere near a rational number with 1,000 in the denominator. Anyway, it's not a hard thing to do. Pretty nifty. And the book kind of gives a computer-generated graph of this Thomé function. And so see page 127. For an attempt. It's a really wild-looking thing. Well, all the theorems we proved about limits now apply to the concept of continuity. And so a very important observation is that we had a sequential definition of limit. And when you apply that to continuous, the definition of continuous function, so here's the sequential criterion. For continuity. Let's suppose I have an f from some subset of the reals into R is continuous at a point C if and only if the limit as n goes to infinity of f of xn equals f of c for every sequence in A that tends to C. With xn in A for all n, and the xn's tending to C. And sometimes if you want to show something is not continuous, then you would have to you could find a sequence that doesn't have this property. That's an easier way to show when something is not continuous. So kind of remark. Useful when showing f is not continuous. So the famous example of a not continuous function is f of x equals, take your pick, how about 1 at the irrationals, zero if x is rational. X is irrational. That's a famous function. Lebesgue, who was studying area and integration, studied that function and realized even though it's 0 lot, the area under that curve is 1. Let's say we're going between 0 and 1. Then there's so many more irrational numbers than rational that the area under that curve is 1. And the Riemann integral wouldn't tell you that. The Riemann integral wouldn't exist for that function. But Lebesgue invented an integral where that made sense, and then the area under that famous function between 0 and 1 would be 1. And it meant that the rational numbers are a set of measures 0. They don't affect that area. Anyway, that's measure theory when you get more advanced. But this function is discontinuous everywhere, at every point. rational or irrational. So it's not like the Tomei function. And you can see that by cooking up sequences. You know, we have the density of both the rational numbers and their irrational numbers. So I could very easily cook up a sequence that's rational, irrational, rational, irrational. And so it bounced back and forth between 0 and 1, and that sequence would tend to, say, a C. And therefore, the function would not be continuous at C, because I got a sequence that does not do what it's supposed to do. Questions about that? Or about anything? My plan is I'll do 3 sections of Chapter 5 before spring break, and then the homework problems about those 3 sections will be due after spring break, the usual Wednesday night thing. That's the plan. And I'll post those problems Monday probably. So you kind of have a weekend off. But you should be reading you need to read 5.1 carefully now, because I skipped things, assuming you sort of, the stuff is fresh in your mind from freshman calculus. Let's see. Oh yeah, my favorite functions I mentioned already before. Here's another example. I'll have purple and orange. So here's y equals minus x. Here's y equals plus x. And if I multiply x by sine 1 over x, sine 1 over x is that wiggling function that wiggles up and down. When it's plus 1, x times sine 1 over x would be on the top curve. When it's minus 1, it would be on the bottom curve. And it would start wiggling like hell, but then it gets squished, like a squeeze theorem. If I give it the value 0 there, that would be continuous. So this is a graph of x sine 1 over x. And using the squeeze theorem like we did when we were studying sequences, you can show, let's see, x sine 1 over x is an even function. Because if I put minus x in there, I'd have a minus x in front, but sine of minus 1 over x would be minus sine of x. So it's an even function. Wiggles like hell, but it gets squished as it wiggles there. So that's continuous everywhere, including 0, if I define it properly. So if I define f of x to be 0, at x equals 0, and x sine 1 over x for x unequal to 0, that's continuous on the whole real line, including at 0. And of course, it'd be dumb if I defined it to be up here at 0, because it wouldn't hook up right. Questions about that one? And if I didn't have that x in there, if it was just sine 1 over x, that would jump up and down between plus and minus 1 and go totally bonkers as I tended to 0. And of course, that wouldn't be continuous there. So maybe I'll mention sine 1 over x is not continuous at 0. Goes bonkers there. But it's continuous on r minus 0.